Hi, everybody. Listen, I'm really sorry I couldn't make it there. I really wanted to be there. I especially wanted to go out to the pubs and have some beer and just hang out with everybody, so couldn't do it. Sorry. Sometimes life intrudes. But I thought you might be interested in having this keynote anyway. So I've recorded it. I've sent it off. Maybe you'll find time in the bar or something. Get Lakos to buy everybody a big round of drinks, and then you can sit around and watch this thing, huh? So, this is the keynote, right? The last programming language. And I'm going to dedicate this to my good friend Kevlin Henney, who, well, you all know what. In the very late 1960s, I got myself a copy of this book, Introduction to Programming. Notice that it doesn't say programming what. This was the book that taught you how to program a PDP-8. This thing. I happen to have a front panel of a PDP-8. I've kept it for many, many years. Put a frame around it because it was quite a keepsake. The PDP-8 was a wonderful machine. I learned how to program it in the 1960s and early 70s. A good PDP-8, let's see, that would be 12-bit word, 4K of Core. Anybody remember Core? And you could turn the computer off and it would remember. Oh yeah, our computers today do that too. It had a 750 kilohertz cycle time. An instruction would execute in about 1.5 microseconds. That was really fast. We could get lots of stuff done in that 750 kilohertz. 4K instructions. We wrote whole time-sharing systems. You could compile Fortran. They had a Fortran compiler that would run in 4K words. Yeah? Amazing machine. It had, 32K words of disk, if you bought the disk. Usually you didn't. Disks were expensive, but if you needed a disk, well, you could get one, and that would be 32K. It was an infinite amount. It was an incredible amount of disk space. We didn't know what to do with it all. Oh, man, we had, thing was the size of a refrigerator. It had many dozens of cubic feet. It probably took a kilowatt or more of power. And if you wanted to buy one, it would have cost you, in today's dollars, about $120,000. Amazing. I have a laptop that I use, little itty-bitty thing, carry it around in a backpack. It has a processor in it with 2.8 gigahertz cycle time. Actually, 2 cores. So what is that? 5.6 something gigahertz, effectively. That's 8,000 times faster. My little laptop can execute 8,000 times more instructions than that PDP-8 could. That PDP-8 could execute one instruction, and my machine now will do 8,000 of them. I have 8 gigabytes of RAM in my machine. That's 2 million times more memory in my little laptop. I have no disk in my laptop. I've got a little over 500 gigabytes of solid-state memory. By the way, do not get a disk again, ever. Right? No laptop you get should have a disk. The difference is astounding. The age of rotating memories is over. My little laptop takes 85 watts at most. It is far less than a cubic foot, and it cost me, well, it was an expensive machine, but it was less than $5,000. Now, if you add up all those differences, 8,000 times faster, 2 million times more RAM, 16 million times more offline storage, it takes 1% of the power, 1% of the volume, 4% of the price, and you multiply all those together and you get this number, 6.4 times 10 to the 22nd. That laptop that I carry around in my backpack is 22 orders of magnitude more powerful than my PDP-8 was. And what have we done with that power? I mean, to put this in some kind of perspective, 22 orders of magnitude, that's the number of angstrom units to Alpha Centauri. What are we doing with that? 20 orders of magnitude in the increase in our hardware, and what have we done with it? We programmers. How is programming different than it used to be back then? We still write sequence statements, selection statements, and iteration statements, assignment, if, and while. We were writing them back then. They had a slightly different form, but that was still sequence, selection, and iteration, and we're doing that today. And we might think, oh, heavens no, we've got objects, we've got modules, we've got all this stuff. Yeah, it's still the same stuff. We are still writing assignment statements, if statements, while loops. Our technology has not grown by 22 orders of magnitude. We've been riding one heck of a ride on that hardware, but not us. Our technology has stayed almost the same. Oh, we've got great tools. But the material we manipulate with our hands, the code, is virtually the same. So, have we seen it all? Have we seen all the languages there are? I mean, let's go through a list of the languages, shall we? I just wrote down a list of languages that in my career I have had some contact with. Fortran, COBOL, Snowball, wonderful string-oriented language, Algol, Simula, Smalltalk, C, C++, Java, C#, assemblers, lots of different assemblers, too many to count, probably dozens. RISC-based assemblers, CISC-based assemblers, little assemblers, lots of them. Pascal, Delphi, Forth, wonderful language, Forth. By the way, PostScript is Forth, just so that you know. Go, B, BCPL, PL1, PLM, APL, Lisp, Scheme, Scala, F#, Erlang, Haskell, ML, Self, Cecil, JavaScript, Ruby, Groovy, Python, Basic, OCaml, Occam, Prolog. Need I go on? The list of languages could be endless. I'm sure that I did not mention your favorite. So, given all of these languages, we have to ask ourselves a question. Have we seen them all? I don't mean not all of them. I mean, clearly, there are going to be new languages out there, and we can't see them all. But have we seen all the types? Are there going to be new languages that are in any way surprising, the way Forth was surprising, or the way Prolog was surprising, or the way Smalltalk was surprising? Are there going to be anything new languages like that? Any new big surprises? I think that's a valid question to ask. I'm not at all convinced that there are any more surprising languages out there. We may have seen every type of language there is. After all, it's been over 50 years we've had time to explore this space. So maybe we've seen them all. We can think about all these languages in terms of their syntax. COBOL, for example. Well, it's kind of in a class by itself, isn't it? Fortran, Algol, C, C++, all similar in the way their syntax is organized. Smalltalk had a very unique syntax. Forth, what a syntax that was. Perl, Lisp. These languages can be broken into syntax classes. Let's call it the Algol class. Algol, Pascal, Delphi. They all had this thing called block structure. This was a syntax and semantic component, which allowed you to declare one function inside of another, and so forth. It was actually the progenitor of object-oriented programming. Most of these languages use a kind of infixed and prefix notation. Function calls are prefix. Most operations are infix notation. Smalltalk. Smalltalk was a prefix-infix notation as well, although there were no direct operators as such. You had to mix the functions and arguments with keywords in an interesting way. You might call it a keyword language. Lisp is a pure prefix language. Function name first, arguments second, surrounded by parentheses, about as simple as you can get. Forth is a pure postfix language. All the operands up front, function call at the end. A reverse Polish notation, virtually. COBOL, an attempt at natural language. Probably the worst idea ever to happen in software. Let's make our programs read like English. That's just about as dumb as it can be. We'd like our programs to be readable. We do not want to force English grammar and sentence structure into our programs. Our programs are, after all, a little more symbolic than that. Fortran. Fortran was an attempt to make the programming language look mathematical. Formula translator. It didn't succeed at doing that, but it was a very successful language. So was COBOL for that matter, but who cares? Logic languages, Prolog for the most part, organized their code in horn clauses, logical and statements that turn out to be computable, oddly enough. So there are many different ways to organize languages by their syntax. Did you know that Conway's Game of Life is Turing complete? That you can actually write programs by putting little dots on a screen and having them execute Conway's Game of Life? I have examples of many algorithms written in Game of Life. I've even got one of the most absurd, the Game of Life, written in the Game of Life. There's another axis that we should be looking at here, and that's the axis of semantic class. Languages can have a semantic class, a paradigm that they follow. For example, structured or functional or OO. Those are semantic classes of languages. We have seen Fortran and COBOL, which are unstructured. They have almost no semantic class at all. You can do anything you want in those languages, pretty much. Structured. C is almost a structured language. It has a go-to, but we tend not to use it. Pascal, a structured language. It's constrained. Direct transfer of control is constrained. OO is another one of these semantic classes, languages that restrict the use of pointers to functions that give you dependency management through polymorphism. That would be an OO language. Functional languages, languages that constrain the use of assignment. These are semantic classes of languages, and we should talk about them. Probably the first paradigm ever was modular programming. This was the idea that files, programs themselves, should not be large. They should be broken up into many small modules instead of being one great big monolithic thing. We could call this discipline imposed upon file size, or maybe program length or module length. There were some spectacular abuses of this in the 1960s, where managers who heard about modular programming told their programmers they were not allowed to put more than 500 bytes in a module. Now, this is back in the day when we counted the size of programs in bytes. What did the programmers do in order to meet this ridiculous constraint? Well, they wrote, 480 or so bytes in a module, and then the last couple of bytes they reserved for a go-to statement that jumped to the next module. Next came the structured paradigm. Dijkstra wrote that wonderful paper, Go-To Considered Harmful. And in this paper he said, look, keep your programs limited to sequence, selection, if statements, and iteration, while loops. Now, he did this because he wanted to be able to prove algorithms correct, and he discovered that if you let goTo be used in an unconstrained way, you couldn't prove anything. But if you limited your program to those three things, sequence, selection, and iteration, you could prove correctness. Of course, nobody paid any attention to that. That's not what other people were interested in. What they got into was this big religious war about how you should never use goTo, blah, blah, blah. Now, since those days, it turns out that we like our programs constructed out of sequence, selection, and iteration because it is, in fact, easier to reason about them. Not so much the provability, just the ability to think about them. So, structured programming was discipline imposed upon goTo, discipline imposed on direct transfer of control. I went and got this, yes. Another paradigm that we're fascinated by is the object-oriented paradigm. Anybody remember this book by Grady Booch? 1988 sometime you wrote this, I think. The object-oriented paradigm, we've had quite a bit of confusion about this. What the heck is it? It's data and methods together. It's a way of modeling the real world. Okay, well, we finally kind of worked out what this OO stuff is. And what this OO stuff really is polymorphism for the most part. Everything else besides polymorphism you could do in C. You could actually do polymorphism in C if you wanted to, but you had to play with pointers to functions to do it, and that's just not a good idea. In fact, the big benefit that a language like C++ gave us was the ability to play with pointers to functions without playing with pointers to functions. The language had a syntax that hid all of those pointers to functions in the vtable, and it didn't even let us see the vtable. We just had to write virtual functions and use inheritance. What OO in the end actually gave us, what OO in the end actually is discipline imposed upon the use of pointers to functions, discipline imposed upon indirect transfer of control. And in exchange for that discipline, we got a benefit. And that benefit was the easy ability to structure our modules so that the source code dependencies oppose the flow of control. In most structured applications, the flow of control points in the same direction as source code dependencies. In a good object-oriented program, and this is how you know it's a good object-oriented program, key dependencies are inverted to point against the flow of control, and that inversion is accomplished through polymorphism. So the OO paradigm is polymorphism, which is discipline imposed upon indirect transfer of control. The functional paradigm, what the heck is that? Well, the functional paradigm, although very old, has become more important because of the multi-core problem, the failure of Moore's law when it comes to processor speed. Now we're going to have to make our processors faster by putting more cores in the chips. We can't seem to increase the clock speed. And because of that, we're worried about lots of concurrency issues. We're hunting for a computing paradigm that is robust in the presence of many threads and many processors. And the functional paradigm is such a paradigm. It's a way of making software much less subject to concurrent update problems. So what is this functional paradigm? Well, the functional paradigm when you boil it down to its lowest common denominator, the functional paradigm is simply this: discipline imposed upon assignment. We're not allowed to assign values to variables. We can initialize variables, but we cannot change a variable once it has been initialized. There are ways to do it, but there's an immense amount of discipline required. You have to open up a transaction and all this kinds of fancy stuff. You have to treat your variables as though they're in a database. In a pure functional paradigm. There's simply no assignment at all. So, functional paradigm is discipline imposed upon assignment. Now, I have ranted about this book before, The Structure and Interpretation of Computer Programs, and I will rant about it again, because this book makes the point about functional paradigm better than I possibly could. It goes on for page after page after page, hundreds of pages, showing program after program after program, table-driven programs, object-oriented programs, all kinds of programs. And then, on page 200 and something, it shows you the first assignment statement. This whole book is written, in at least the first half, is written without an assignment statement. And it apologizes for the assignment statement. The authors go to great lengths to tell you how awful this assignment statement is, how it ruins the model of computing. If you want to understand the functional paradigm, this is the book to read. And understand what they're saying in here, and you'll get the idea behind functional. So, functional is discipline imposed upon assignment. All these paradigms, and in all of them, nothing new is added. The paradigms, each one, takes something away from programming. It doesn't add anything new. They are constraints, not additions. The paradigms add nothing. They do take stuff away. If paradigms are constraining rather than additive, how much is there left to take away? Maybe we've even seen the last of the paradigms. Maybe there aren't any more. And if there are more, what's going to be left? We've taken away direct transfer of control, indirect transfer of control, assignment. What's left? Is there some paradigm that we've missed? I did not talk about aspects, and with intention. Aspects were not a paradigm. They did not remove anything. They constrained nothing. They added. The whole notion of aspect-oriented program did not decrease our ability, did not decrease our expressiveness. It increased our expressiveness. It added new capabilities and features, and it failed. Nobody's doing aspect-oriented programming except in a couple of little niches. It's not like that was the revolution that took over, and it's not likely to be. So, paradigms subtract. They do not add. And there just isn't a lot more to subtract. So, maybe we've seen the last paradigm, too. Somebody out there is saying, yeah, but what about graphical languages? We just really haven't done the graphical thing. Oh, yeah, we have. We've done the graphical thing over and over and over again. We have explored graphical languages inside, outside, sideways, in, and over. And in every case, they've kind of been disappointing. Does anybody remember Prograph? You know, the 1980s, Prograph, the Gunakarra Sun Systems, this thing on the Macintosh that would let you do, it was an object-oriented graphical language. It would let you write object-oriented programs in a data flow style. Whatever, and this didn't go anywhere. Anybody remember Helix, the great database language on the Macintosh? Beautiful data flow kind of way of setting up queries. What happened to that? Nothing. Model-driven architecture. It's nowhere, yeah. I mean, we have had some success with finite state machine modeling, although that's even better in a table than it is in a diagram. There are a few that are kind of interesting, you know, educational things like Chipwits that's kind of fun to play with, but no, graphical languages just have not happened. And there's been plenty of opportunity, and they just don't happen. There's probably something about programming and text that is so well aligned that the whole graphical thing doesn't work. Maybe it's because when you're programming, time is linear. Time is linear in a program, and so we think of our code as being linear. In an algorithm, time goes in one direction, so that's one-dimensional. Text. Shouldn't our languages be textual? I know there's all this talk about other kinds of languages, graphical languages and that kind of thing, but shouldn't our languages be textual? And after all, mathematics is textual. Most sciences are textual. The notations involved in math and science, generally textual notations. So, shouldn't programming be textual too? I'll give you a rationale. Algorithms occur as a sequence of events. The execution of an algorithm is one-dimensional. Time runs in a single dimension. So it is probably natural to model it as a sequence of statements, a text. Electronics, well, yes, that's graphical. There's lots of stuff going on at the same time, flows of current here and there, but that's not true of programming. Programming occurs one step at a time. And even when we talk about multiple concurrent threads, the stuff happening inside those threads are happening one little step at a time. It's one-dimensional, textual. So, shouldn't our programming languages be textual? Now, I'm sure that some of you out there have already begun to think about domain-specific languages. What about them? I mean, we're always going to have lots of domains, aren't we? And of course, that's true. We are. Domain-specific languages are going to be an important part of our profession for years to come. And in fact, it's probably a growing important part of our profession. As the number of domains proliferates, we will have more and more domain-specific languages. And in fact, we should strive to choose to use domain-specific languages rather than general-purpose languages for many different applications. However, no domain-specific languages will ever replace general-purpose languages. And that's what we're really talking about in this discussion. We're talking about general-purpose languages. Fine, we'll have lots of domain-specific languages. They will proliferate. We'll have gobs and gobs of them, and we should. The question is, how many general-purpose languages will we have? Now, you might ask the question, well, general-purpose languages just aren't that important if we have lots of domain-specific languages. I disagree. I think that the vast majority of code written in the coming decades will be in general-purpose languages. Oh, there will be plenty of DSLs, and they'll be important, but it's the general-purpose languages that get the real work done in major enterprise applications, and in any kind of application for that matter. All right? We're always going to have general-purpose languages. So, the question is, how many do we need? Have we seen them all? So, what if we've seen the last language syntax? I mean, there will always be different syntaxes, but what if we've seen the last class of syntax, the last meaningful class of syntax? Is there any point in searching for more at this point? I mean, when was the last major syntax revolution? Certainly it wasn't Java. Certainly it wasn't C#. It wasn't Ruby or Python. It wasn't Clojure. The last big syntax revolution may be Prolog. Probably fourth. It was a long time ago. Are we going to see another? I have my doubts. So, what are the hot new languages right now? There's Scala. That's a language that's got its roots back in the 70s. It came from a funny language called Funnel. Who's ever heard of Funnel? And before that, of course, it was derived from ML. So this is a language that has its roots in the 70s. That's an old idea. Okay, it's on top of the JVM. That gives it a little bit of spice, but F#, well, it's kind of a variation on OCaml, which is again a variation on ML, and a variation on something called iSwim. Well, whatever, 1966. Again, you know, old stuff. And another hot language right now, Closure. It's Lisp. It's Lisp. 1957. Our hot new languages are not new. They're old. They're based on old stuff. Again, are we done? Have we seen it all? When our hot new languages are just old stuff, doesn't that tell us that we've kind of closed the loop? We've come full circle? That there really isn't anything else out there? Maybe. So, what is the hot new paradigm? It's functional now, right? That's the new one. Functional programming. And why? Well, because of the multi-core problem, because Moore's Law and all of that stuff, right? Now we're all interested in functional programming. It'll save us from concurrent update issues. This paradigm is old. It's ancient. It's got its roots in Lisp, 1957. It's got roots in ML from 1970s, and it's the hot new thing. There's something odd about this, right? The hot new thing is 50 years old. So I'm beginning to think that we've seen them all. That there aren't any more languages, meaningful languages to explore. We've seen the logic languages and the structured languages and the functional languages, and I think we've seen them all. And one of the reasons I think that is because we keep coming back to the old ones. We keep coming back to Lisp.
Simple but fun, guaranteed to blow your mind.
Remember Lisp.
Minimal and sequence just so clever you will breathe.
Remember Lisp.
Lisp is the language that won't die. How many times have we tried to kill this language? How many times have we took swords out and cut all those parentheses and they keep coming back? Lisp is the language that will not die. Think about Emacs. Holy cow. Emacs, this editor that is immensely powerful. Immensely powerful, why? Because it's got Lisp inside it. It's got a nice implementation of Lisp that lets you do just about anything. For a while, I thought maybe the big IDEs were going to have the upper hand. Of course, they do at the moment. I'm starting to think, though, that these Emacs guys are just going to keep chewing away and chewing away and chewing away and just blow past all these IDEs. Because this language, Lisp, and this editor based on Lisp, it's not going to die. There's an old saying when it comes to Lisp. It's called Greenspun's 10th Law of Programming. You've all heard it before, but it's worth repeating. Any sufficiently complicated C or Fortran program contains an ad hoc, informally specified, bug-ridden, slow implementation of half of Common Lisp. Who among us has not seen that? So, what if we decided to just choose one language, end this menagerie of languages that we've been using, and pick one or two? We would certainly not be the first industry to have done this, and many industries have decided to unify their notations. Maybe it's time for us to admit that these are notations and not religions, and pick the notation that satisfies us the best and use it. Certainly mathematicians have done this. There used to be dozens of different mathematical notations. Now, for all intents and purposes, there's just one. Biologists did this. There were lots of different biological nomenclatures. Chemists have done this. Many industries eventually get to a point where they decide enough of the babble, enough of the Tower of Babel, the millions of different languages, it's time to just pick one and use that one. And think of the benefits of doing this. I mean, suddenly we would have all papers written in one language, all programs written in one language. Can you imagine? No more worries about whether a module was written in your language or not. You could just use the language. Imagine the benefits that have happened to physics and to mathematics and to biology and chemistry simply because we unified notation. Maybe we would experience a similar kind of renaissance of research and progress by unifying our notation. So I think there is quite a bit of benefit to be gained. But there's something else. There's yet another reason why we should unify, and that is no corporate control of languages. The end of corporate enslavement. I'm a conservative. I believe in the market. I'm a Republican in the United States, but having these big corporations own our languages is awful. It's terrible. They use the languages as levers to twist things and contort things. We, the programmers, have lost control of our very mode of expression. That's not acceptable and has to be stopped. It has to be done away with. Now, it's not hard to do away with this. We're programmers. We have the power to completely eliminate it. We could write our own language if we wanted to. Many of us have. Many of us are. We could write a language and just do away with the corporate ownership of languages, and we must. At some point, this corporate ownership of language has to end, because we don't want to be the pawns of Oracle or Microsoft or IBM. We want to be able to express ourselves in a language of our choosing, not some corporation's choosing. So what's the likelihood that we could actually pick a language? You know, a bunch of programmers, getting them all together to choose a language is sort of like herding cats. Well, what encourages me about this is that we've done it before. We have chosen languages before. Not quite as globally as I'm talking about here, but consider the language C. C dominates every language we use nowadays. Think of Java and C# and C++ and even Ruby, dominated by the C syntax. We chose a notation with C. The C notation, one way or another, has become the de facto standard. Even in something like Ruby, we see C notation permeating all through it. So we are not incapable of making these kinds of unifying decisions. It may be time for us to do a little bit more than choosing bang equals for not equal. It might be time for us to instead of double equals or something like that, it might be time for us to do something more, some grander choice where we actually pick a language, but I think we are capable of doing it. So let's say that we did pick a language. What would that language look like? What would its characteristics be? Maybe we can get some insight on this by looking at some languages we know. For example, would this language be C? Well, there's some problems with C. It's not garbage collected. Do we really want to go down that path again? You can't do reasonable polymorphism in C. I mean, you can hack the pointers to functions, but God help you if you do. It's compiled down to a real machine. There is no virtual language for C. It just seems out of focus with where we are now. We don't want to be tied to hardware any longer. The language does not allow you to modify it while it's running, and you cannot, fiddle around inside the running C program while it's running. It's not homo-iconic. C++, what about that? That's all the same problems that C has, and boy, is it syntax heavy. Wow, learning all that syntax is just horrible. And now, the standards committee has just gone completely ape. They're just adding syntax, lots of little fiddly stuff in there. I think I'd rather not learn all that stuff. Java. Well, it's not a functional language. It doesn't have the solution to Moore's law that we're all hoping for. So Java, it's a pretty good language other than that, but it's a little syntax heavy. Maybe we should do something better than that. C#, same thing. Same thing. C# and Java, I mean, no difference. They're the same language. So, what should the language look like? What should its attributes be? So, what semantic class should this language belong to? What paradigm should it support? Should it support just one or all of them? Should it be a functional language? Should it be a structured language? Should it be an OO language? Or many of us would probably prefer that it was a hybrid language. But let me make this statement about hybrid languages. When a language belongs to all semantic classes, it doesn't belong to any of them. Because remember that paradigms, semantic classes, are about restrictions. If your programming language allows you to do assignments, then it's not functional, even though it might allow functional programming. Scala, for example, is not a functional language. You can do functional programming in it, but the language itself does not force the paradigm. C is not a structured language. You can do structured programming in it, but it's got to go to. So you can do non-structured programming in it. C++ is not an object-oriented program because it has pointers to functions. And if you can deal with pointers to functions in the raw, you're not an object-oriented language. So the hybrid languages keep all the power that the paradigms have been trying to constrain. Hybrid languages don't belong to any functional class. They aren't paradigm-based languages. They are anything languages. They're unconstrained languages. What do we want our language to be? Do we want it constrained? Or do we want it to have all the power? The power! Spock here. Another thing we want out of our languages is simplicity. And by that I mean simplicity of syntax. Think of a language like Forth. There's almost no syntax. Think of a language like Smalltalk. Almost no syntax. Or Lisp. Again, almost no syntax. Just lots and lots of parentheses. Now think of a language like C++. Now, I love C++. I do. A wonderful language, but there's syntax there. Think of Java, syntax. Think of Scala, syntax. I think we've had enough of the syntax-heavy languages. I think we've had enough of language lawyers. It would be awfully nice if our language had a very simple syntax so that we could focus on semantic issues instead of syntax issues. Still, another attribute of a programming language that I think we want is polymorphism. We want dependency inversion. We want to be able to control the way our modules depend upon each other. We want to be able to set up our modules so that the source code dependencies oppose the transfer of control, the flow of control. And that's what polymorphism gives us. So any language we choose should have polymorphic ability. But that's not what an OO language is. An OO language gives us a constraint. It says we can't use pointer to functions. We must instead do our dependency management solely through polymorphism. I think this is important. I think we want our languages to be polymorphic and constrained. I think we want the discipline imposed upon indirect transfer of control. And we want our language to run in a virtual machine. This is another lesson we've learned over the years. We don't want to be bound to the hardware. We don't want to know about the hardware. We don't want to have to always run our machine on an Intel platform when there's all these other platforms out there. We want to be able to run on any platform, pardon me, that we want to. And so we want virtual machine. Whatever language we choose should be a virtual machine language. Whatever this language is that we choose, it should also have access to all of our frameworks. It should, for example, work with the JVM. It should be able to work with Java. Java should be able to call it, and it should be able to call Java. C# should be able to call it, and it should be able to call C#. The major virtual frameworks that are out there should be able to work with this language without any problems. We obviously don't want to divorce ourselves from the vast libraries of functions that have been created. We don't want to throw away these massive enterprise frameworks. So whatever this language is, it will have to be able to work with those frameworks well. And there are a few contenders. I mean, there are versions of Ruby that work on both of these platforms. There's versions of Python that work on both of these platforms. There's Groovy that works on the Java side. I don't think it'll ever go on the .NET side. And there's Clojure that works on both sides as well. So we want a language that fits in all of the virtual frameworks that are out there so that we can maintain access to our libraries. I think we want this language we choose to be structured. And by that I mean it should not have a go-to. It should impose discipline on direct transfer of control. I think we want it to follow the structured paradigm, which means it can't be C or C++. They have go-tos in them. Right? We want this discipline imposed upon direct transfer of control. So Java, there's no go-to in Java, although they do have those dumb numbered breaks. Dumb. C#, I think there's a go-to in C#, but nobody uses it. Clojure, no go-to. Ruby, no go-to, as far as I know. We can do languages without a go-to, and I think this language that we choose, whatever it is, should not have a go-to. And another thing we've learned is that we want our languages to be garbage collected. We've learned our lesson on this. We don't want to be doing manual memory control anymore. My God, how many times have we been rebooting at midnight because of horrible memory leaks and stuff like that? We've learned our lesson on this. And Apple, are you listening? I mean, Objective-C? Really? Objective-C? How old is this language? 1979, Brad Cox invents this thing, and it almost died. We almost got rid of it. It was in the garbage can when Steve Jobs pulled it out of the garbage can and resurrected it. God help us forever. Anyway, garbage collection. We want our language to be garbage collected. Good. This is excellent. Good. Hello, Twinkles. What did the room animal? Oh, yeah, the room animal. Oh, yes. Whatever language we choose, we want it to be fast. C is fast, right? We want a language that really moves. Yes, I know. We want it to move along quickly. We want it to be a snappy language. C is a fast language. Assembly language, fast language. C++ is a fast language. Ruby, not so fast. Python, a little faster. Clojure, pretty fast. Quick language. F#, fast. Scala, fast. Basic, slow. We don't want these slow languages. It's going to have to be snappy. The next thing we want is a language that is symbolic. We don't want the language tied to the hardware. We don't want it to be like a machine language or even have any of the trappings of the hardware. We'd like our language to be symbolic, abstract. C is a language that is too close to the hardware. We know that an int, for example, is 32 bits. C++ has the same problem. Even Java has bits of that problem. It's close to the metal. Well, that's tough to say Java's close to the metal, but it has trappings that are close to the metal. Smalltalk is a language that's not at all close to the metal. Clojure is a language that's not at all close to the metal. Ruby, not even close, right? So we'd like our languages to be abstract so that we're not coupled to the notion of hardware. And then finally, we want our languages to be textual. We've tried the symbolic language before. We've tried the graphic language, We've tried the graphic languages before, and although they're interesting, they just don't really do it for us. And something about the programming domain, like the mathematical domain, is textual in nature. There's something serial about it. There's something one-dimensional about it. The reasoning inside of a software module is one-dimensional. It proceeds in a direction in time. So it's not at all clear that a graphic language is what we want. We probably want a textual language. Yeah, that's right. That's right. Okay, yeah. Another language attribute that I think we want is homoiconicity. I know, that's tough to say. We want our languages to be homoiconic. In other words, we want the languages to be able to manipulate themselves. The running program ought to be able to construct more running program or alter more running program, just like a machine language program can do. And just like most Lisps can do. We want this ability to be able to manipulate the code while it's running. Ruby has some of this capability. We call it monkey patching or meta programming. Even Java has a small bit. You can manipulate bytecodes, but God, who wants to? So whatever language it is that we choose probably should be homoiconic. By the way, Ruby is not homoiconic. Neither is Java. Oh yeah, you can reach in and fiddle with the bytecodes or goof around with the Ruby inheritance and class structures, but that's not quite the same as saying that the code is the data. The data is the code. That's a very powerful statement, and I think we want our languages to have that capability. So what language is it that meets all these criteria? What language would I choose if I had to choose today? Probably Clojure. It's the only one that meets all the criteria I've outlined. I think it's a good language. I think it's an interesting language. Will it be the language? Oh, probably not. Probably not. We will probably continue to twist and turn in the wind for a while. But I imagine that we will choose a language soon. And by soon, I mean some number of decades where that number is probably larger than one. I presume we will choose a language. I presume that language will have all of the features I've just outlined. It might even be something that looks like a Lisp, maybe like a Clojure. So, take a look at Clojure. See if you think it could be the last programming language. Well, so thanks everybody. I appreciate you watching, and sorry I couldn't be there. I really wanted to be there and have a few pints and listen to some great talks, but I hope you enjoyed this one. I wish I could have delivered it live. Guys, have a lot of fun, and maybe I'll be able to get there next year. I sure hope so. Talk to you all later.